Hello. In this lecture, I will be covering two topics: units and unit conversions, and kinematics in one dimension. I will begin with units. As you might know, there are two systems of units in the world. One is called the System International, or International System of Units, SI. And then there is another one called the US Customary System, or the British system, or the imperial system. I want to talk about both of them and how to convert from one to the other. The basic unit of measurements are three. You have time, length, and mass. And I'm going to give a symbol of a bracket with a capital T to indicate this is a unit of time, and a bracket with a capital L as the unit of length, and then a bracket with a capital M as the unit of mass. Okay? Now, so if I put them down here, if I make a table, and with two columns here, one for the SI, the International System of Unit, and the other one is for the US Customer System. So the units here, we have the time, T, length, and mass. In the SI system, the basic unit of time is the second, okay? And the basic unit of length is the meter, and it has the symbol M, small letter M. And the basic unit of mass is the kilogram. In the US customary system, the time is also a second, but the basic unit of length is the foot or feet. Okay? It's not inches, it's the foot. And the basic unit of mass is called the slug. Don't confuse it with the pound. The pound is different from the slug. More on that later. Back to the SI system. In the SI system here, there is actually two subsystems to it. One, we refer to it as the MKS, and the other one is the CGS. Okay? What does that mean? MKS stands for meter, kilogram, second, and the CGS stands for centimeter, gram, second. You see that? So if we said that the SI system has three units, second, meter, and kilogram, but they can also be used, there are two subsystems. One is the meter, second, meter, kilogram, and then they can also be centimeter, gram, and second, okay? And so this is the meter, kilogram, and second, and this, or it can be used as centimeter, grams, and second. The thing is that you can use either of the subsystems. Either you can use meters, kilograms, second, or you can use CGS system. However, you never mix the two, okay? Which means, for example, you cannot say something has a mass of so-and-so kilogram and a length of something in centimeter. You cannot do that. Or something that has a mass of so-and-so grams and has a length of 2 meters, for example. You cannot do that. You cannot mix the two columns together. You can either use this column or this column exclusively, but you don't mix the two, okay? That's the key here. All right, let me show you some examples on how this works, or in other words, how do I convert from, say, SI unit written in the SI to units written in the US customary system, for example. Okay? We'll begin with an example here. Suppose that the speed of an object, say a car, is going at 130 kilometers per hour, and I would like to know what is the speed in, say, miles per hour. Okay, so what do? Well, first you need to find a conversion factor, or a conversion way, a way to convert kilometers into miles, okay? And you can look up your book, or you can look up the web. I have one right here on my desktop. Let me just open up for you. And as you can see here, if you look at the length right there, you will notice that 1 mile right here is equal to 1.61 kilometers. So that's the one I'm going to be using, all right? And the way you do that is simply you go back to the problem that you're dealing with. So here we have 130 kilometer per hour. Of course, I am converting the kilometer, but I am keeping the hour. So in this case, I'm going to put a bar here. And since I want to get rid of the kilometer and I want to replace it with mile, so what I do is I want to put the kilometer at the bottom as a denominator right here, okay? The reason I'm doing that because I want to get rid of it. And I'm going to replace it with what? With miles. So I put the miles here. I'm going to call it MI. And now I look at the relationship between mile and kilometer. And it says here 1 mile is 1.61 kilometer. So I go back here. So 1 mile is 1.61 kilometer. And so as you can see here, the kilometers will cancel out. And I'll end up with... so here's the speed. Oops, I reached the end of the screen here. Anyway, so we have the speed is 130 miles per hour. You see that? So I go, so it has 130 over 1.61. I can use my calculator for that to convert it. And I have 130 divided by 1.61. And answer is equal to 80.75 miles per hour. And there we go. I got it. Okay. Another way, let's see, another example. Suppose that I have the same speed here, but I'm being asked to find what is the speed in, say, meters per second. Okay. So here we converted it from from kilometers per hour to miles per hour. Now I want to convert it to meters per second. So convert speed equals 130 kilometers per hour to meters per second. How would you do that? Well, in this case, as you can see, I am converting 2 units. The hour into seconds, and the kilometers or kilometers into meters. So I'm going to write it down like this. Speed is equal to 130 kilometers per hour, like that. And then because I'm converting 2 units, I'm going to put 2 bars, okay? 1 bar for converting the kilometers into meters, and the other bar is for converting the hour into second. You get that? So because the kilometer here is in the numerator, I'm going to put my kilometer, the one I want to eliminate with, at the bottom right here. Okay? And then I have the hour is in the denominator. I'm going to put my hour right here in the numerator in the second bar. You got that? So I have here hour. And of course, I'm converting hour into second, and I'm converting kilometers into meters. And now I get the relationship between them. I hope you know already what they are. But again, you can look up a conversion table. I'm not sure if it's here on this. I have just a small conversion table here. I know it's not here. I don't see it. Anyway, I hope you already know that, well, we know that 1 kilometer is 1,000 meters, correct? And of course, 1 hour is 3,600 seconds. Okay, the reason is because 60 times 60, right? 60 minutes times 60 seconds, that would be 3,600 seconds. Okay, so I have those conversion factors right there, and I just need to plug them in. So here I have 1,000 meters is equal to 1 kilometer, and 1 hour is equal to 3,600 seconds. Now make sure your units cancel out properly. So I have here kilometer cancel out, hour cancel out, and I'm left with what? I'm left with meters per second, and that's what I'm looking for. So I need to now use my calculator to calculate 130 times 1,000 divided by 3,600. I hope you're working with me. So I'm going to do that. So it's going to 130 times 1,000 divided by 3,600. Answer 36.11. So I get 36.11 meters per second. Okay? And there we go. This is how I convert that. Okay? Okay. One more example. I'm looking up some notes here. Here's an interesting one. Suppose, for example, let me just move this a little bit to the side. Okay. So the example says, suppose the mass of a solid cube is equal to 856 grams, okay? And each edge of the cube, that is 5.35 centimeter. And the question is, find the density. Okay, find the density in kilogram per meter cubed. Kilogram per meter cubed. Okay, so we want to find the density. We're going to call the density the Greek letter rho. Find it in kilogram per meter cubed. All right. So since you're given different units, he basically gives you the chemist's unit. Chemists always use grams and centimeters, and physicists use kilogram and meter cubed. So what I want to do, there's so many different ways of doing it. So the way I want to do it is I basically want to get, since I'm given gram and centimeters, the CGS system, I'm just going to get the density in gram per centimeter cubed, and then later on I will convert it into kilogram per meter cubed. Okay? You can do it in a different way. That'll be fine, but that's how I'm going to do it. So we know that the density, rho, is equal to mass over volume. And then volume, I know that because it's a cube. Looks something like that. And each side, let's call that L, L, L. And each side is equal to 5.35 centimeters. So the volume is L cubed, so that will be 5.35 centimeter cubed. And when I use my calculator to calculate what is the volume of the cube, so it's going to be 5.35 to the power of 3, and the answer is 153.13 centimeter cubed. Okay, that's the volume. I got the volume. And now I'm given the mass already. It's right here. So I can easily find the density, right? So here the density in this case is going to be mass over volume. So that will be equal to, the mass is equal to 856, 856, so that's 856 grams divided by the volume is right above me. It's 153.13 centimeter cubed, and then I would just get divided by each other. 856 divided by 153.13, answer. If I did it correctly, it is 5.6 times, that's it, 5.6, sorry. That's 5.6, what? Gram per centimeter cubed. And there we go. I have found the density is equal to 5.6. Let me just say 5.60, okay? So the next step now is I want to find the answer, or I want to convert the unit into kilogram per meter cubed. So how do I do that? Well, we do the same thing, but before I do it, see, I am going to convert centimeter cubed into meter cubed. This is maybe the hard part, maybe, okay? How do I do that? Well, what is the relationship between meters and centimeters? I know that 100 centimeter is equal to 1 meter, okay? All right, so what is 100, how about centimeter cubed? So how do I do that? The easiest way to do it is you basically cube both sides, like this. So when you cube both sides, you're going to get 1 meter cubed, and that will give me what? 10 to the power of, what is it? 10 to the power, I think I'm making a mistake, hold on. So let me just analyze it. So I have here 100, whoops. I have 100, which is 10 to the 2 centimeter cubed. And now when I insert the cube in there, that's going to be 10 to the 6 centimeter cubed equals 1 meter cubed. I hope this is clear for everybody. You see that? Okay, so now I have a relationship between them. Of course, I know that also, that I already know that 1,000 gram is equal to 1 kilogram. So I need that conversion as well. Now back to my density answer. I know that rho is equal to 5.60 gram per centimeter cubed. And I'm converting 2 units. I'm going to have 2 bars like that. 1 bar for the gram. So I'm going to put the gram at the bottom because this is already on the top here. And then the gram is going to convert into kilogram. And the centimeter cubed at the top. I'll put a bar here. And I'm converting it into meter cubed. Now I'm going to put the relationship. 1,000 gram is 1 kilogram. And as you can see right here, 10 to the 6, which is a million centimeter cubed, is equal to 1 meter cubed. So now when I convert them, I just use my calculator. Well, before I do that, let me make sure that the units eliminate. So the gram will go away, centimeter cube will go away, and I'm left with a kilogram per meter cube, and that's what I'm looking for. So now I'm going to multiply. So I'm going to multiply. Let me put them in different color just to show you. So I'm going to be multiplying 5.6 divided by 1,000 times a million. You got that? So that's what I'm going to do. So that's going to be 5.6 divided by 1,000. I'm sure there is an easier way to do it, but that's just one way to do it, I guess. And that will give me 5,600 kilogram per meter cubed. Okay? And there we go. I have converted the density from gram per centimeter cubed into kilogram per meter cubed. Okay? Okay, good. One more example before we finish this part of the lecture. I want to switch to black color. Okay, the question says, it says if, well, the universe's age, is 13.7 billion years old. Okay, there are two parts for the problem. The first, what is the age of the universe in second? Okay. So how do we do it? Well, we know that the age of the given to us is that the age of the universe is 13.7 billion years. Now, when we say the word billion, that means it is 10 to the power of 9 years. Okay, a billion years, which is in computer language, something like a giga. So we can say a giga years, G-E-Rs. Okay, a giga year, so 10 to the 9. Now, I want to convert it into seconds, so that means I want to convert years into second. You see what I'm saying? So the billion is there, but I want to convert the years. Well, how do I convert the years? Well, I know that, again, we are talking here about Earth years, right? How do we convert it? Okay, you can start from the number of days in a year, and then you convert the days into hours, and the hours into minutes, and the minutes into seconds, and there we go, right? So we can say that in 1 year, there is 365.5 days, is that right? And 365.5 days, I'm going to call them D. You multiply this by 24 hours, that will give you how many hours per year? Excuse me, how many hours? Yeah, this is correct. How many hours per year? And then you multiply that by 60 minutes, that will give me how many minutes per year? And then you multiply by 60 seconds, that will give me how many seconds per year? You see what I'm saying? So when I do that, so let's go ahead and calculate all of this. So it's going to be 3,600 times 24 times 365.5. Answer, I'm going to get 3.15 times 10 to the 7 seconds. Okay? And by the way, I've always memorized this number. Notice that the number 3.15 is roughly pi, the pi value, times 10 to the 7. 7 is kind of an easy number to remember. So that would be approximately 1 year, roughly. This is how I remember it. Pi times 10 to the 7 if you want to memorize it. But anyway, so there we go. So we have here, here is the number of seconds. So now this is for 1 year. Well, he said the age of the universe. Let me call the age of the universe tau. Let's just give it some symbol. So I'm going to give it the symbol, the Greek letter tau for time. And so that means it's 13.7 times 10 to the 9 years. That's the age of the universe, giga years, if you will. So that's 13.7 times 10 to the 9. I'm sorry, I should put this over 1. So I need to convert. So I'm going to convert what? I'm converting years into seconds. So I have here 1 year. I should just say year rather than years, the plural. And then here I have 3.15 times 10 to the 7. And then when I multiply that, so that's going to be times 3.15 times 10 to the 7. Of course, the years will cancel out, and I end up with only second here. See what I'm saying? So when I multiply that times 10 to the 9. And that will give me 3.15 times 13.7. My fault. There we go. So we have here, if I did everything correctly, I'm going to get 4.32 times 10 to the power of 17 seconds. So that's the age of the universe in second. I hope this is easy. There's nothing difficult about it. Now the second part of the problem, so this is the first part of the problem, said what is the age of the universe in seconds. Now convert, now there's another question here for part B. It says convert 4.7 times 10 to the 12 seconds into years. Okay, it's just a number. You pulled it out of the hat. Okay, so how do we do it? Well, the same thing. So I have here, I already know the conversion factor. It's right here. Right here. 1 year is 3.15 times 10 to the 7. I'm not sure if my my little conversion chart here has it for the time. No, I don't have it here. Anyway, there we go. So here we have, so I have here 4.7 times 10 to the 12 second over 1, and I'm converting the second into years. So the second's going to go down, and then the year here. And so what is the conversion between them? Well, we just derived it right here, right there, right? So that's going to be 1 year, 3.15 times 10 to the 7. The seconds cancel out, and that will give me 1.49 times 10 to the 5th years. Okay? Or I can write it if I want to. 149,206 in more details if you want to. And there we go. Okay? Okay, I think that's all I wanted to talk about regarding conversion of units. Now I want to move on to kinematics in one dimension. Okay, so the next topic is kinematics in one dimension. Okay, when we say the word kinematics, how is it different from the word dynamics? Okay, kinematics and dynamics and the study of mechanics are basically all means the study of motion. But kinematics means the study of motion without asking what caused the motion. Okay, that's the key here. Is that we're not asking what caused the motion. Of course, what causes the motion later on is, you will learn, it is the force. Okay, so that's what causes the motion, or what causes the state of motion of the object to change. Okay, but when we say kinematic, we're just saying what is, we are basically describing the motion of the object, and we usually describe it with the speed of the object, the velocity. It could be initial velocity, it could be final velocity. We are also describing it with how far did it go, for example, in terms of x, the distance or displacement. We're also describing it in terms of time, how long the object has been moving, or how long it will go until it reaches its destination or whatever. Also, we are asking, well, how fast it is. It's not just how fast it's going; it's how fast it's speeding up, which we call an acceleration. Or what's the rate of deceleration, which is how much it's slowing down. So that's deceleration. So these collectively together, the velocity, the distance or displacement, time, and acceleration, these collectively are called the kinematic variables. Okay, and more on them later because there are an associated kinematic equations associated with that. We're going to talk about that later. But for the time being, these are basically the variable that we use to describe the motion of an object. Okay, and once we use those without asking what's causing the motion, we are really into the realm of kinematics. Okay, the word kinematics here. So we're going to cover kinematics in two parts: kinematics in one dimension and kinematics in two dimensions for this course. All right. So let me begin with kinematics in one dimension, and I will start with a very simple example. Imagine, for example, an object moving. So here is a straight line. Think of it like the x-axis, for example, or say it's the street, but it represents an the x-axis. Here's the x-axis here, and imagine an object is here, and it moves. Let's say it's initially at t equals 0. We're going to call it t1 equals 0, which is the initial position of the object at t1. We'll call it. It is at position x1 equals 0. Think of it like the origin of the x and y axis. So we have an x and y axis like this. Here's the x-axis. Here's so initially the object is right here at the origin. Okay, I don't need to draw the y-axis because we're dealing with one dimension. All right, and the object is moving, right? So it's moving. Let's say it's moving to the right, and with certain speed, certain velocity, and after some time t, now the object is here. So it is at a later time. We're going to call that t2, okay? At a later time. Suppose the number, let's just put a number to it, say 15 seconds. So after 15 seconds, the object is here. And of course, the position of this object here is x2, let's say, I'm copying it from my notes here, 10 meters. Okay, so the object traveled for 10 meters. Started from 0 meters right here, and it traveled for 10 meters. All right. Now, assuming that the object is moving at constant speed. So let's just suppose that the speed is constant. Okay, which means we're not talking about acceleration here. We're ignoring it for now. All right. And now the question is, what is the average speed of the object? Okay, what's the average speed of the object? Let me make it a little bit. I'll give you a real life example that is related to what I have just shown you. Suppose that I am right now in Las Vegas. Okay, and I am going to travel to LA. Okay, and let's suppose that the distance between Las Vegas and LA is 300 miles. Okay, and I tell you that I started traveling from, here's my car, and I started traveling from Las Vegas on this highway. Suppose that the highway is straight. It goes directly into downtown LA. It's a straight highway. And let's suppose that I did not change my speed. I just kept going non-stop at the same speed. Okay. And it took me, let's say, 5 hours, for example. So it took me a time of 5 hours to get to LA. All right. Now, the question is, what was my average speed? Well, if you remember back in the 8th grade when you studied physical science class, they taught you speed is equal to distance over time. And that's a cool formula, provided that you can use this formula anytime you want, provided that the acceleration is 0. There is no speeding up. You're not speeding up or slowing down. You're going at a speed. So this formula is valid when acceleration is 0. Okay, so if you don't have acceleration, that's a valid formula. You can use that. Okay, so so when I calculate the speed, so basically the distance is 300 miles divided by 5 hours. So that will give me what? I was traveling at an average of 60 miles per hour. And there we go. That's my average speed. You see what I'm saying? Simple, right? And this above example that I'm just showing you is identical to that. There is really no difference whatsoever between them. Okay? So now, when I ask the question, what is the speed? So we define the speed to look something like this, rather than writing it in distance over time. Again, which is a cool formula. There's nothing wrong with it. But I want to write it in a fancier notation. Delta x, excuse me, erase it. Delta x over delta t. What does that mean? It means x2 minus x1 over t2 minus t1, okay? So what that means, velocity, or my speed here, so I go back to the notation that I have created here, right there, this notation in here. So if I plug in all of that, so I have x2, which is 10, minus 0, divided by t2 is 15, minus 0, and then when I calculate that, I will get 10 over 15, which is what, 2/3, and that would be 0.67 meters per second. There we go. This is the speed of the object going from this location x1 to this location x2 within a time span of 15 seconds. You got that? So the speed is 0.67. Now, if I want to graph this thing, let's suppose I want to graph this on an XY plane, and the graph should look very familiar to you. So if I put x and y, sorry, not x and y, I wanted to say x and t, or tx rather, t and x. So remember, I have the time, see that? I have the time right there, t1 and t2. So if I put those on the horizontal axis and x1 and x2 on the vertical axis, and remember in physics we always put the time axis and the horizontal, okay? So anyway, so if I have that, and if I would plot those 2 points, so we started with t1 x1 right here, 0, 0, correct? Here it is right there. And here, right there. And then t2 x2 is 10, 15. So let me plot that 10, 15. So so let's suppose 15 is here, 10 let's say is here, and let's say the point is right there, okay? So I have here what I have a line that looks something like that. Remember the shortest distance between 2 points is a straight line. So I can draw a line that represents my motion here, okay? If you remember the slope of the line, how do I find the slope of the line? The slope, as you know, slope, if I can spell it correctly, so we have the slope is equal to what? Remember delta y over delta x. So I'm going to apply it to ours here. It's delta x over delta t. And guess what? What is delta x over delta t? It's basically the velocity. See that? So the slope of the line, the one that you've learned in algebra, is nothing but the velocity. All right? So this is how you calculate the velocity. Basically, you get the slope of the line. So here I have here 15 right here, 15 in second. This is all in second, and this is in meters. And I have here 10 meters right here. And so I can calculate the slope in this case, okay? And the slope will give me the velocity equal to 0.67 meters per second. And there we go, okay? Okay, let me give you a better example to show you how all that applies. The example from a textbook, I'm going to show you the picture. The textbook. Where is the textbook? Oh, it should be here. There it is, right here. So what I have the following figure. So you have here something like a timeline. So you have, this is the x-axis, this is the t-axis, and then we have an object started at t equals 0. So remember, this is a time at t equals 0, it was already at a position of 25 meters, okay? And then remember, if there is a slope, then this is speed. So this is a positive slope as well, so it's moving, let's say, to the right. So the object moves to the right until it reaches, a distance until 50-meter mark. So that means it has traveled from 25-meter mark to 50-meter mark. So it has traveled for 25 meters. And then what happened here? Well, that's the horizontal. Which is the slope of a horizontal line? That's a 0. That means it stopped. For how long did it stop? Well, from 20 second to 30 second. Okay, and then here we have a negative slope. That means what? It went backward to the left. Remember, this is positive slope. It means it moved to the right. Okay, and we can calculate the speed of that. We'll talk about it in a minute. And then it moved to the left. But look at that. The slope here is steeper. It's negative, and it's also steeper than this slope, which means it moved to the left faster. And from the 30th second until the 40th second, which means for 10 seconds it moved, and then it came back and it stopped at the 0-meter mark. Got it? Okay. So let's work it out. So the problem here says, let me look it up. It says here, problem number 4. He said figure 2.4 is the position versus time graph of a jogger. Okay, so we have a jogger. What's the jogger's velocity at t equal 10 seconds, t equal 25 seconds, and at t equal 35 seconds, okay? I hope this is a simple problem for you. Let's work it out. You can pause the video and draw it, please, before I move on. So I'm not going to draw it in my note, but you can pause the video and draw it. I can put it on the side here, where you can hopefully see it on the screen right there. I can move this here. There we go. I'll just leave it like that. How about that? Okay. So we have this problem. So at t equals 10 seconds, and look at the t equals 10 seconds. The 10-second mark is right here. So basically he's asking, what is the velocity right here? Well, the velocity right here is basically the slope of the line. Make sense? So all I need is really to calculate the slope of the line. And to calculate the slope of the line, all you need is 2 points on the line segment. So I have this line segment, and I need just 2 points. So I can take this point right here and this point right here, okay? And so if I'm going to call that, so you have x here and this is t. So basically the velocity is equal to delta x over delta t. And the points in this case is going to be, for the axis, x2 minus x1. So that's going to be 50 minus 25. Is that okay? That's going to be 50 minus 25 divided by what is the corresponding time for that? The 50 is 20. And the 25 is 0. So that's going to be 20 minus 0. And then we calculate that. And that will give me 1.25 meters per second. There we go. So the speed of the jogger here in this region, he was going 1.25 meters per second. Okay? All right. Or at the 10 second mark, her speed was 1.25. All right. Now, the next question, he said, what about at the 25 second time? So we have here at t equals 25 seconds. Again, we do the same thing. Where is the 25? Well, the 25 is right here in the middle. Should I make it big? There we go. The 25 is right here. So basically on the line segment, this one, I can put in the answer very quickly. I hope you see that. It's 0 because it's a horizontal segment and the slope of the horizontal line is 0, okay? But let's just act like we don't know that. Let's just do it. So in this case, I'm going to pick 2 points. So the point I'm going to pick is this point and this point. So the coordinate for the x is going to be 50 minus 50 divided by 30 minus 20. Does this make sense? So that's going to be, of course, going to be 0. So delta x over delta t. So it's going to be 50 minus 50 over 30 minus 20. And that's, of course, 0 meter per second. So here, basically, jogger stopped moving. You see what I'm saying? It's not moving. All right. And then the next one at t equals 35 seconds. Okay. So the 35-second mark, which is basically right here somewhere, right? In the middle. So it belongs to this line segment. Before I do anything, I can tell that this line segment is a negative slope, right? A negative slope, that means the jogger is moving to the left. In other words, he's returning back. You see what I'm saying? Here initially, he was going to the right for 20 seconds and traveled 25 meters. Stopped, took a break for 10 seconds, took a sip of water or whatever, and then returned back, but faster, sprinting maybe sprinting for the next 10 seconds and stopped right there, okay? So that's the story of his motion. So anyway, so we have that. So the velocity in this case, all I need is to pick 2 points. So I can pick this point right here and this point right here, okay, the coordinate of it. So that's going to be v equals to delta x over delta t. And when I pick it, let me make it small. It gets even bigger. How do I make it small? Oh, what's that? There we go. There we go. Okay, so you're looking at the graph. So I'm going to pick 2 points. I'll start with the x's. So I'm going to start from 50 and the 0. Well, the 0 the second. So it's going to be 0 minus 50, correct? So it's going to be 0 minus 50. That's why you get that negative. Is divided by 40 minus 30, correct? That's positive, so it's going to be minus 5 meters per second, okay? Notice that the speed of the jogger initially was going 1.25. Now it is almost 3 times that fast. So he's really going much faster, 3 times, okay? So this is negative slope. Or you can say that jogger moves to the left. Okay, here positive slope, and here jogger moves to the right. You see what I'm saying? Okay, great. Okay, let's do one more problem. Well, several more. I want to do number 11 point, number 2.11. Excuse me. So let me look up the book for this. Number 11, right here, this graph right here. Look at it. You can pause the video and draw it if you want to. Okay, so here what makes the graph different is not xt axis, but vt. You see what I'm saying? Okay, so before I do this problem, let me just show you something quickly. Something that you have already studied in calculus, maybe. So before I do it, I want to just give you one quick example here of, I'm trying to find it. Sorry, bear with me. There we go. Suppose, okay, this is again from calculus. If you haven't taken calculus 3, this is, but I'm sure you've studied that or you've seen it in the past. So suppose I have a position vector, or let's just say a displacement function x of t equals to 6t squared plus 5t plus 2. What is that? What is that? That's a displacement function or a distance function. What that means is, let's suppose I have an object, and the object is is the motion of that object described by, say, this function, f of t. I should call it x of t, sorry. Okay, well, this is the time axis, and this is the x of t here. Okay? Okay? So if I want to know what is the position of the object, say, at this time right here, at some time t, say 2 seconds. And I want to know the position of the object on the 4 seconds. I want to know the position of the object at, say, well, it's not supposed to be negative. Sorry, this is probably incorrect here. I'm just going to be start from here. Let's just start from here. Okay, let's say I want to know on the, say, 0.1 second and so on. How do I know that? What's the position of it? Well, all you need is just plug it in. So, for example, on the second, okay, so I can just go x of 2 is equal to 6 times 2 squared plus 5 times 2 plus 2. That'll be 6 times 4 plus 10 plus 2. That's 24 plus 10 plus 2. And that's 36 meters. In other words, on the second, the object has traveled 36 meters. On the 4th second, the object traveled whatever it is. Just plug it in. Okay, this is called a distance function. Okay, a fancier term for it is a position vector. Okay, but that's for later. Okay, this is called a position vector. It basically gives you the position of the object at any point in its trajectory. Okay, that's the meaning of it. Now, all right, so I know the position of the object at any point t. What about if I want to know the velocity of the object at any time t? What about the acceleration of the object if I want to know, at any time t and all that? Well, it's simple. The way you do it is simple. If you are given the position vector or the distance function x of t, then the velocity function is basically the derivative of the position vector. You see what I'm saying? Or the distance function. And the acceleration, oops, I reached the edge here. And the acceleration is the derivative of the velocity function, like this. Okay? In other words, those are things that you really need to memorize and understand very well. Extremely important stuff. Okay? So let me go back to the equation that we have just written. So we have x of t is equal to 6t squared plus 5t plus 2. So what is the velocity function? Simply take the derivative of it, and that will be 12t plus 5. There it is. See what I'm saying? And what's the acceleration? 12. You can put whatever units you want, but that's basically how you do it. In other words, let me make the drawing again. So I go back. Here is my drawing of the. Let's say I have it like this. Okay. Again, this function is not representative of this one. I haven't thought about how to draw that, but this just to say, suppose that this is it. Okay. So this is x of t, where this is x of t here, and this is t right there. Okay. And then what I want to do, I want to know the velocity. Okay. Well, the velocity is this. It's basically a straight line, right? 12t. That's the equation of the line. So if I want to know, if I say what is the position at 2 seconds, we already did the calculation for that. It's right here, right? So the position of the particle is equal to 36 meters. In other words, the particle after 2 seconds have traveled 36 meters. You got it? What about the velocity of the particle on 2 seconds? Well, plug it in here. So that will be 12 times 2 plus 5. So that will be 24 plus 1. That's 29 meters per second. Okay? What that means, on the second, the particle or the object has traveled 36 meters and its speed at that moment is 29 meters per second. What about this acceleration? Well, according to the formula right here, the acceleration is a constant, meter per second squared, we can say here. So the acceleration of the object on the second is 12 meters per second squared. I mean, in other words, it is speeding up at a rate of 12 meters per second. Okay? That's really the meaning of those formulas. Got it? Okay. Let me give you a quick example before I go back to this example right here. Okay, let's say, for example, I have, that's just an example from my head. Let's say I have v of t equals to 2t plus 4. Okay, this is the velocity function. Okay, this is my velocity function. Okay, I want to know what is the position function. Okay. Now, usually when you have a problem like this, usually they give you more information about it. They will say something like, let's suppose, given that at t equals 0, okay, the position function of the object is 0. Okay, suppose that this is given to us. What does that mean? What that means that initially, in the beginning, at t equals 0, the object was located right there at the origin. All right, that's the meaning of it. Why do I need this piece of information? I'll tell you in a second why. All right, so I am given the velocity function right here. He's asking me for the position function, this one. Well, I know that the derivative of the position function right here, the derivative of the position will give me the velocity. So what is the position function is equal to if I know the velocity? Well, it's just an integral, correct? So I'm going to integrate in this case. All right, so therefore, x of t is equal to the integral of v of t dt. I hope this makes sense to you. Okay, so far? All right, plug it in. So let's see how we do that. So the integral v of t, of course, is given to us right here, 2t plus 4. dt. Okay? Integrate, so that's going to give me t squared plus 4t plus what? The constant of integration. Remember, your calculus teacher always taught you, whenever you integrate, always put that constant, right? I don't need to explain to you why. I hope you understand that. So I'm going to call that c for now, okay? This is the notation your math teacher would use. So there we go. We have x of t equals that, okay? Now, if you were in a math class, you would have been basically done, and you would have moved on to the next problem or whatever. You're done with the problem. Well, in physics, you can't end a problem like that. Or in engineering, somebody's going to ask you, what is that c? Well, it's a constant. Well, what is the value of the constant? Remember, at the end of the day, as an engineer, you need to come up with a number, a real number that they can use. You can't just say, oh, the number is 5, 6 plus c. Well, what is c? Okay? So you have to find the value of this c. Again, your calculus teacher never told you to find it. You just put a c there and you move on to the next problem. But in physics and engineering, you must find that value. You can't stop. This is not enough. You can't box this equation yet. Got it? So how do I find it? Well, this is where this part right here is given to us. He didn't give you this for free. He said, given that at t equals 0, x of 0 equals 0. This is called, in mathematics, it's called the initial condition. It's a good word, good term to remember. The initial condition. There is also something called the boundary condition. But that's a big field in mathematics, the initial condition. So the initial condition is given to you. Why is it given to you? Because it will allow you to calculate the constant of integration. Okay, that's the whole purpose of the initial condition. This is very important to know that. Okay, so I'm not done yet. So now the next step is I need to find C. Okay, I need to find C. How do I find it? Apply IC, initial conditions. What is it? It says at x of 0 equals 0. That's the initial condition. It's right there, given to us. Okay? Remember, this 0 right here is the time. So I need to go back to this one. So I go x of 0 equals 0 squared plus 4 times 0 plus c equals what? Equals 0. Well, I'm going to get c equals 0. Okay, so at least I know c is 0. So therefore, my final answer, x of t, will be t squared plus 4t. And there we go. Here is my position function. You got it? Okay, good. Okay, now back to problem number 11. Trying to find it. Back to problem number 11. I keep moving on the, let me move the screen a little bit more so I can draw it. I reached the edge of the oh, this is not even clear. Okay, let's go back to the book. It says here, so we have this diagram right there. It says in the figure shows the velocity graph of a particle moving along the x-axis. Okay, I mean, remember the x-axis is not there. Remember this graph. Look at it. It's v velocity here. It's not displacement. It's not x. It's not position. Okay, so vt, not xt. You see what I'm saying? Okay. So these are seconds, first second, second second, third second, and these are velocities, 2 meters per second, 4 meters per second, 6 meters per second, and so on, okay? All right, he said its initial position at x naught equals 2, okay? He tells me that, okay? This is his initial, its initial position is 2.0 meter at t equals 0. Why did he give me this one? Initial condition. In other words, I'm probably going to be integrating something, all right? And this, I'm going to be using it for something, all right? And at t equals 2 seconds, which is right here, the second, but he said, what are the particle's position and velocity and acceleration? Okay? So you may want to pause the video, pause it, and then look at the problem, try to understand it, try to digest it before you look at my solution. So let me repeat it again. So you're given VTX, a VT graph, and you have a line that looks like that. He said this is the velocity graph of the particle moving along the x-axis. The initial position at t equals 0 is equal to, it started at 2 meter mark, if you will. And on the second, what is the particle's position, velocity, and acceleration? That's what he's asking me to do. Okay? All right. I'm going to move it on the side. Hopefully you'll be able to see it. I think it's chopped off. Right there. I have to move this a little bit like this. Okay, so let's do it. I can find the acceleration very quickly here. How do I do that? Oops. How do I do that? The acceleration, well, before I do that, let me make a drawing of it. Let me just draw it and then write down what's given. So I have something like this. This is 3, 0. This is the time axis. This is the velocity axis in meters per second. and the point here is 0.06 meter per second, that is, and that's the origin, of course. Okay, now I can find the acceleration. How do I find the acceleration? Well, the acceleration is the slope of the line, the slope of this line in the VT axis. In other words, acceleration is delta V over delta T. Okay, I hope you already know that from your book. Okay, so I can find the acceleration. All right, so I can pick 2 points. I'm going to pick this point right here and this point right here. And when I calculate, so that's going to be something like 0 minus 6 divided by 3 minus 0. So the acceleration is minus 6 over 3. Acceleration is negative 2 meter per second squared. Okay? So I found the acceleration of the object. What that tells me is that the object is slowing down. Okay? So you started here at t equals 0. Remember, this is 0. Started here at t equals 0, and then it's slowing down until stopped, if you will. Okay? And the acceleration rate is 2 meters per second each second. Okay? That's the meaning of the minus sign. It's slowing down. All right. Now, what else I can get out of that? Well, from back to algebra, I can, if you give me any line, let me go back to algebra. Okay? Suppose I have, this is x and y. And let's say I have a line like this. Okay? And I'm asking you to find the equation of this line. If you remember this formula, it's called the point slope formula. Y minus y1 equals m x minus x1. That's pure algebra, if you remember, where m here is the slope, and x1 and x1 and y1 is any point, any arbitrary point on the line. Okay, and that will give you the equation of the line. So I want to do that. Okay, but I'm not given the position and time. I'm given the velocity and time right here. So I want to use this formula for this graph to find the equation of the line in the v in terms of velocity. Okay, in other words, if I take this and write it in terms of my notation here, I'm going to look something like that. So find the equation of the line. Find equation of the line. So that's going to be something like v minus v1 equals slope, which is basically the acceleration. I hope you believe that. T minus t1. Please make sure you understand what I have just written. It's very similar to that. Okay, basic algebra. Okay, and so I'm going to pick 1 point. So let me pick, it doesn't matter which one. You can pick this point, 3, 0, or 0, 6. It doesn't really matter. You should get the same answer. So I'm going to pick the upper point right here, 0, 6. Okay? Remember, the 6 here is v, and the 0 here is the time. Got it? And the slope, of course, is right here. The acceleration, that's the slope. Remember that? So this is the slope. Okay, so plug in all of that in there. That's going to be v minus v1 is equal to 6 equal the slope negative 2 0. Excuse me, this is t minus 0, correct? Okay, so t minus 0, and so I have v minus 6 equals minus 2t, or v equals minus 2t plus 6. And there we go. I have the velocity function, which is very similar to the velocity function that I have done right here. Remember when we do an integration and to find the position function? Here it is. I have the velocity, and from that velocity, with this boundary, excuse me, the initial condition, I was able to find, integrate, and then I was able to find the distance or the position function. Okay, that's exactly what I'm going to do right now. Okay, so I already got in the velocity function. Here it is. I'll come back to it to answer some of the questions, but I'm now concentrating on finding all of them. So here's the velocity function. So I need to find the position function or distance function. Position function. And the position function is x of t, which is the integral of the velocity function. Is that right? So that's going to be integral of negative 2t plus 6 dt. Again, I'm going to be applying the initial conditions to find the constant of integration when I do that. Anyway, so let's do it. So that will give me integrating. So that's going to give me minus t squared plus 60 plus the constant of integration. Is that right? Okay, in physics we don't write c, we write something like x naught. Okay, that basically constant of integration. And if I'm integrating for velocity, it will be something like v naught and so on. Okay, so this is the constant of integration. And I need to find it. I don't know what it is. You see what I'm saying? But that's basically the position function right there. Now I need to apply what I need to apply IC, initial condition. So let's go back to what he said about the initial condition. Sorry, I need to go back to the problem. I thought I'd written it down. Right here. He says the its initial position is x naught equal 2 at t equals 0. Okay, this is what I want. That's exactly what I want. Okay. So my initial condition here is x naught equal 2 at t equals 0. So I'm going to plug it in there. I have x of 0 equals 0 plus 0 plus x naught equals to x naught, right? And that's equal to 2, and that gives me x naught equal to 2. So therefore, x of t is equal to minus t squared plus 60 plus 2. And there we go. This is my position function. Got it? Okay. Now, let's go back to the question that he's asking. He says, at t equal 2 seconds, what are the particles' position, velocity, and acceleration? So all you need to do, I already found the velocity function right here. Right here. Let me put them in different color. I'll put pink. All right. So the velocity function, v of t, is equal to negative 2t plus 6. That's the velocity function. A of t, I already got it. It's a constant right here, the very beginning. Okay, this is A of t is equal to negative 2 meter per second squared, right? It's a constant, you see what I'm saying? And then I have x of t is right here. So now he said, back to the problem, he said at t equal 2, what are the position and all that? Okay, so simply x of 2, that's going to be negative 2 squared plus 6 times 2 plus 2. That's negative 4 plus 12 plus 2. And that will give me 10 meters. Okay? And then what about the velocity? Velocity of 2. Again, I go back to that equation right here. Negative 2 plus 6. So I have negative 2. Negative 2 times 2, excuse me, plus 6. So that's negative 4 plus 6. So V of 2 is equal to 2 meters per second. And of course the acceleration is constant, is equal to, I forgot what it is, negative 2 meters per second squared. And there we go, I have them all. Okay, and basically I have a full solution of the problem. You got that? Okay. Okay, in the next video, I will be talking about kinematic equations and free fall.